In this video, we're going to look at a few more examples of optimization. We're going to be using calculus to find optimal solutions to these problems. And of course, we're going to be focusing on building appropriate models for this problem. And for this one, it should say the fence along three sides is to be made of material that costs $6 per foot. Let me add that here. Along one side, the fence will cost $18 per foot. Okay, all right, so this is the problem that we want to solve. Okay, so find the dimensions of the rectangle that will allow for the most economical fence to be built, or basically we want to minimize our cost. Okay, so first thing I need to do is let's just sketch a little picture. Okay, this is the fence that we're talking about, and that little wavy line represents the fancy side. Okay, so we might call this L, this is also L, this is W, this is W. And they tell us what the area needs to be. So area is equal to length times width, or we can say 800 is equal to length times width. All right, we're trying to minimize cost, so we need to come up with an expression for cost. So in general, we're going to have the cost for the $6 fence plus the cost for $18 fence, right? So for the $6 fence, okay, we've got to use 2 of the widths and 1 of the length, right? So we're going to take 6 and multiply it by 2W plus L. Okay. And then for the $18 fence, $18 per foot fence, then we're going to have plus 18L. Okay. So we got 12W plus 6L plus 18L, or 12W plus 24L. Okay, this is our cost function. But we really want this in terms of one variable, not two. So we could either solve for L or W over here in the area formula. Okay, so let's say 800 divided by W is equal to L. Okay, so that means I can replace L with 800 over W. So we get 12W plus 24 times 800 over W. We got 12W. This is going to be a cost function just in terms of W. Okay, so 12W plus 24 times 800 is 19,200, and I'm going to go ahead and write that as W to the negative 1. Okay, all right, so we're ready now to take the derivative. C prime of W equals 12W minus 19,200 W to the negative 2. Okay, and so we want to set this equal to, when we take the derivative, this would be just 12. Okay, we're going to set that equal to 0. And so we get 19,200, or negative 19,200 over W squared equals negative 12. Okay, we can solve that. It's basically going to come down to W squared is equal to 19,200 over 12. And so we get W squared is equal to 1600. And the square root of that is going to be 40. So W equals 40. Okay, so we want to make sure that this is indeed a minimum. So we need to take the second derivative. So C double prime of W is equal to 38,400 W to the negative 3, or we could say over W cubed. Okay, so I can look at this and tell that C double prime of 40 is going to be greater than 0, which means at this point we are concave up and we have a relative minimum, right, which is what we want. Okay, so this is our proof that this thing does indeed yield a minimum. So the question that we need to answer is, what are the dimensions of the rectangle that will allow for the most economical fence to be built? Okay, and so we know that W is equal to 40. We're looking for dimensions, W by L. So it's going to be 40 by, well, we know we can get L by looking at 800 over 40. So that's going to be 20. All right, feet, both in feet. So the dimensions that will allow for the most economical fence would be 40 feet by 20 feet. Notice, it makes sense that we would use the least amount of fencing possible for the side that is $18 a foot, right? So that we can minimize our costs. We've already ensured that we're going to meet the constraint of the area, right? We said L times W has to be equal to 800, but notice that L, we're using less fencing on that side than on the W side, which is going to help us to reduce our costs. All right, let's look at one of these problems where we are considering an increase in something, okay? We saw a problem similar to this where we were looking at the number of trees that we plant, right? How many trees should we plant to maximize our yield? When we consider that the more trees we plant, the yield per tree is going to be reduced, okay? So this is a similar problem. It says a 300-room hotel in Las Vegas is filled to capacity every night at $80 a room. For each $1 increase in rent, 3 fewer rooms are rented. If the cost to service a room is $10, how much should the management charge for each room to maximize profit? What is the maximum profit? Okay, so our goal here is to maximize the profit. And the thing that we need to make a decision about is how much to charge for rent above the $80 per night price. Okay, so I'm going to let X be the number of $1 increases in rent. Which means that the rent for a night is 80 plus X. Okay. All right. And if we're talking about profit, we need to know how many of these rooms we're renting, right? So we can also use X for that. What it tells us is that every time we increase the rent by $1, then we have 3 fewer rooms available, right? So how do we use that to say how many rooms there are? Well, if we start out with 300 rooms, okay, and we, let's say, let's let this be X. If we have a $1 increase, then we get 297 rooms, right? That's equal to 300 minus 3 times 1. Okay? And if we got 2 rooms, it's going to be what? 300 minus 3 times 2, or $294, right? If we got 3 rooms, it's 300 minus 3 times 3 rooms. Okay? So $291. So if I rent X rooms, or if we have X dollars of $1 increases, then how many rooms do we have? It's going to be 300 minus 3x. Okay, that's the number of rooms that we are renting at the new price. Okay, so 300 minus 3x, number of rooms rented. Okay, so now it's time for us to come up with our profit function. We know that profit can be found by looking at revenue minus cost. And our revenue is going to be the rent per night times the number of rooms rented. So we have $80 plus X is our rent per night, and 300 minus 3X as the number of rooms rented. Okay. Now, we do have an expense, and that is the $10 fee to service a room. So we're just going to take 10 and multiply it by the number of rooms that are rented, which is 300 minus 3x. Okay, so we could multiply all of that out if we wanted to, or we could maybe factor out this 300 minus 3x. Okay, that's going to leave me with 80 plus x minus 10, or 300 minus 3x times 70 plus x. Okay, that's my profit function. All right, now we're going to go ahead and find our derivative. So P prime is the first times the derivative of the second plus the second times the derivative of the first. Okay, so we'll simplify that. 300 minus 3x okay. Let's write it out. Plus, or rather minus 210 minus 3x. Okay, so we get 90 minus 6x. That's my derivative. Okay, if I set that equal to 0, then we get x is equal to 15. Okay, so that's my critical value. Does it give me a max or a min? Well, I'm going to take my second derivative, which is negative 6. So this thing is always concave down, which means we have a max. Okay. All right. So that's what we want. Okay. So we know we have a max when x is equal to 15. So the questions are, how much should the management charge for each room to maximize the profit? Okay. Well, we said the rent per night is 80 plus x. If x is 15, we're going to charge 80 plus 15, or $95 per night. Okay, and then how many rooms? No, that wasn't the question. The question is, what is the maximum profit? So if I want to know what the maximum profit is, I'm going to plug 15 back into my profit function. I can plug it in at 300 minus 3 times 15 times 70 plus 15. So we get 300 minus 45 times 85. I got $21,675 as our maximum profit. All right, let's look at one more problem. And this is one of those problems where we've got expenses based on our production cost of a production run, and also storage cost. Okay, this problem is pretty simplified in the sense of the distribution of the books throughout the year is going to be equal. Okay, so we don't need to think about, oh, well, this is a slow period, so we're going to have to store this set of books longer. We're just assuming that the distribution is equal. We're assuming that when we get ready to do another production, we have depleted all of the books from the previous production by selling them or doing whatever it is. Okay, so those are the assumptions. Those may not be most realistic, but for us, those are the ones we can work with and solve. All right. So a publishing company sells 50,000 copies of a certain book each year. It costs the company $1 to store a book for 1 year. Each time that it prints additional copies, it costs the company $1,000 to set up the presses. How many books should the company produce during each printing in order to minimize its total storage and setup cost? All right. So we're going to start by saying X is the number of books to be printed during the production run. All right. And then Y is going to be the number of production runs. Okay. And Y is always going to be that. Okay. Number of production runs. Okay. And X is going to be something very similar. Okay. It's the number of items to be produced during the production run. All right. When we do this, X times Y has to meet our need for the year. So by having X books printed per production run and Y production runs, at the end of the year, we would have produced a total of 50,000 books. Okay. All right. So now we're ready to start looking at our cost. Okay. We've got cost based on what it cost us to set up the presses. So, or basically for each production run. So our cost is going to be 1,000 times Y, plus we got to look at the number of books that we're storing. Okay. And there's a lot of explanation for this. But during each period, we've got an average of X over 2 books in storage, right? And then we have so many periods per year. But we'll always say the number of books in storage is X over 2. We can talk more about this. Okay, and then the cost to store that is $1 per book per year, right? But this is just for one of our production periods. Okay, so by the time we add up all of our production periods, then that would account for a year, and it works out. Okay, but this is the basic way that we will set the problem up. Now, we run into the same problem that we've seen before. In this function, we've got two variables, X and Y. We're not ready for that, so we need to reduce this to just one variable. So we could say that Y is equal to 50,000 over X. Okay, or we're going to say C of X is equal to 1,000 times 50,000 over Y, or rather over X, plus X over 2. Okay. All right, so we get 50 million over X plus X over 2. Or we could have written this as C of X is equal to 50 million X to the negative 1 plus 1/2 X. All right, so now we're going to this is my derivative. Now we're going to set the derivative equal to 0 and solve. So we're talking about 50 million over x squared, negative 50 million over x squared equals negative 1/2. Okay, or x squared equals 100 million. And so x is going to equal 10,000. Okay. All right. We want to verify that this is indeed a minimum. So we'll look at the second derivative. Which is going to be 100 million x to the negative 3. All right, that's our second derivative. All right, which if we plug in 10,000 for that is going to be positive, greater than 0. Okay, which means it's concave up, and therefore we have a relative minimum. Okay, so x equals 10,000 is our number. How many books should the company produce during each printing in order to minimize its total storage and setup costs? And our answer is 10,000 books per printing.